Everyone, today I Jyoti of class MSc Chemistry first year is here to read out a chapter for visually impaired candidates, and this is unit 4 of physical chemistry, and the name of unit is electrochemistry. So let's start. First topic is Debye-Huckel limiting law of activity coefficients and its limitation. The idea of ions in electrolytic solutions and their mutual interactions was taken for granted. However, the conceptual understanding of these electrolytic solutions thrived via a different route. Initially, the scientific community through that the electrolytic solutions are the same as the non-electrolytic ones. In other words, they did not pay any special attention to the charged species and therefore treated him just like the non-electrolytes. Derivation of Debye-Huckel limiting law. Classically, the partial molar free energy mu I of the ith species is non-electrolyte is given by the following reactions. Mu I is equals to mu naught I plus RT ln xi, equation 1, where mu naught I is the partial molar free energy when the concentration xi is the unity standard state. Mathematically, we can say that if the xi is equal to 1, mu I is equals to mu naught I. At this point, it is worthy to point out that the Coulombic interaction long range can be neglected in the case of non-electrolytic solutions, which is obviously due to the uncharged or the neutral nature of the solute particles. However, some short range electrostatic interactions like the London dispersion forces or the dipole-dipole may play a significant role in the average interparticle distance is small enough. This means that if the dilution is large enough, the ion-ion interaction, large range Coulombic effects can be simply ignored in non-electric solutions. Thus, in equation 1 is valid only for those solutions which is known long range electrostatic interaction occur, and such solutions are called as ideal solutions. However, when the equation 1 was applied to the electrolytic solution, it was found that mu I is equals to mu I minus mu naught I is not equal to RT ln xi, which is equation 2. Such solutions which shows deviation from equation 1 are called for non-ideal solutions. This means that unlike non-electrolytes, the ion-ion interaction must be considered before any theoretical treatment for the chemical potential of ionic solutions is carried out. Therefore, to rationalize this deviation, the scientific community developed a unique approach even before the Debye-Huckel's ionic cloud theory. They tried to quantify the deviation from the idealistic behavior by incorporating an empirical parameter Fi in the equation 2 as mu I minus mu naught I equals to RT ln xi Fi, equation 3, where mu I is the partial molar free energy when the concentration xi and the correction factor Fi both are unity. Mathematically, we can say that if xi is equals to 1 and Fi is equals to 1, which is obviously mu I is equals to mu naught I, a hypothetical situation in which standard state behaves ideally. Moreover, it should be noted that xi represents the actual concentration of the ions of the ith type, which may or may not be equal to the expected concentration because weak electrolytes do not dissociate completely like the strong one. After that, it was assumed that it is not the actual concentration xi but the effective concentration xi into Fi that dictates the chemical change. For simplicity, the effective concentration of the ith species was simply labeled as the activity Ai. Mathematically, we can say Ai is equals to xi into Fi, which is equation 4. The correction factor Fi is also called as the activity coefficient, has a value of unity for ideal solutions, that is when Fi equals to 1, Ai equals to xi. Consequently, the partial molar free energy change in going from the ideal state to the real state in the ionic solutions can be written as mu I minus mu I naught equals to RT ln xi plus RT ln Fi, which is equation 5. The above equation is an empirical formulation of the behavior of ionic solution and cannot give any theoretical result for Fi. Therefore, in order to find out the physical significance of the activity coefficient, we need to assume an ionic solution that can be switched from ideal non-ionic interaction to the real situation with ionic interaction. For ideal solution, when we have mu I ideal equals to mu I naught plus RT ln xi is equals equation 6. For ideal solutions, mu I real equals to mu I naught plus RT ln xi plus RT ln fi, which is equation 5. The chemical potential change from ion-ion interaction can be obtained by the subtraction of equation 6 from 7. Mu I real minus mu I ideal equals to del mu I minus 1 equals to mu I naught plus RT ln xi plus RT ln fi minus mu I naught minus RT ln xi, which is equation 8. Del mu I naught minus 1 equals to RT ln fi, equation 9. Hence the activity coefficient is a measure of chemical potential change due to the interaction of the ith types with the rest of the ionic species. Now, according to the Debye-Huckel theory of ion-ion interaction, the partial molar free energy change due to ionic-ionic interaction, that is del mu I minus 1 equals to minus Na, which is Avogadro number Zi square E naught square into K divided by 2E is equation 10, where Zi is the charge number on the ith type of the ion, while E naught is the electronic charge, Na is the Avogadro number, and E is the dielectric constant of the surrounding medium, that is solvent. The symbol K with Ni naught as the bulk concentration. K equals to 4 pi by E into K into T summation I N I naught into Zi square into E naught square to the whole power 1 by 2, which is equation 11. Now from equation 9 and 10 we have RT ln Fi equals to minus Na Zi square E naught square into K by 2E, which is equation 12. The above result implies that the Debye-Huckel ionic cloud theory enables us to determine the activity coefficient in a theoretical framework. Furthermore, if the actual concentration of the ith type of the ion is represented in the terms of molarity or the molality, the equation 6 takes the form mu I equals to mu naught I into C plus ln C1 RT, which is equation 13. Mu I equals to mu 1 naught into N plus RT ln Ni, equation 14. Similarly, for real solutions, equation 7 takes the form mu I equals to mu I naught into C plus RT ln Ci plus RT ln Fc, which is equation 15. Mu I equals to mu I naught into M plus RT ln Mi plus RT ln Fm is equation 16, where mu I into C plus mu I naught into M are corresponding standard chemical potential at a molarity Ci and molality Mi respectively. At this point, some experimental limitations must be discussed before any comparative analysis of the activity coefficient is carried out. It is a quite well-known fact that we cannot measure the hydration energy, that is non-solvent interaction of individual ionic species, because the addition of only cations or anions is not possible practically. Even if it was possible, it would result in negatively or positively charged solution depend upon the nature of the ions added, which eventually would cause desired interactions. Owing to similar argument, it also practically impossible to measure the activity coefficient Fi, which is also a function chemical potential change arising from ion-ion interaction. The only way to avoid the situation is to add the electroneutral electrolytes to the solvent, which would eventually produce the positive and negative ion simultaneously, irrespective of whether it is strong or weak. Therefore, one can determine the activity of a net electrolyte consisted of minimum 2 ionic species, and we need something that can connectivity coefficient of electrolyte with the individual ionic species. All this resulted in the idea of mean ionic activity coefficient. To illustrate mathematically, consider a NaCl type univalent electrolyte Ma. The chemical potential of the cations M positive and anions A negative can be written as mu into M positive equals to mu naught M plus RT ln Xm plus RT ln Fm plus equation 17. Next is mu A negative equals to mu naught A negative plus RT ln XA negative plus RT ln FA negative, which is equation 18. Now combining the equation 17 and 18, we get mu m plus mu A negative equals to mu naught m plus mu naught A negative plus RT ln bracket xm plus x A negative plus RT ln bracket fm plus fa negative, equation 19. The above equation gives the free energy of the system due to the 2 moles of ion, that is 1 mole of M positive and 1 mole of A negative, or due to 1 mole of electroneutral electrolyte. Since we are interested in the average input to the total free energy due to 1 mole of ion only, therefore we must divide the equation 19 by 2, that is mu M plus mu A negative divided by 2 equals to mu naught M plus mu naught A negative divided by 2 plus RT bracket start xm plus x A negative to the power 1 by 2 plus RT ln bracket start fm plus fa negative to the power 1 by 2, equation 20. Mu plus minus equals to mu m plus mu A negative by 2, equation 21. Mu naught plus minus equals to mu naught m plus mu naught A negative by 2, equation 22. X plus minus equals to x m plus x A to the A power negative to the whole power 1 by 2, equation 23. F plus minus equals to bracket start f m plus f A negative to the whole power 1 by 2, equation 24, where mu plus minus and mu naught plus minus are the mean chemical potential and standard mean chemical potential respectively. The symbol X plus minus and F plus minus represent the mean ionic mole fraction and mean ionic activity coefficient respectively. Here it is also worthy to note that mu plus minus and mu naught plus minus are simply the arithmetic means, whereas x plus minus and f plus minus are the geometric equation mean quantities. Now using value from equation 21 to 24 into equation 20, mu plus minus equals to mu plus minus mu naught plus minus plus RT ln x plus minus plus RT ln f plus minus. This is equation 25. Since it is for 1 mole, instead to 1 by 2 into mu Ma equals to mu plus minus, which is equals to mu plus minus naught plus RT ln x plus minus plus RT ln f plus minus, which is equation 26. Hence the experimental value of f plus minus can be obtained just by knowing the free energy of 1 mole of electrolytic solution at a particular concentration. Once the value F plus minus is known, the product of individual activity coefficient can be obtained using equation 24. The individual values of activity coefficients obtained from equation 12 can be put in equation 24 to compare experimentally observed values so that the Debye-Huckel model can be tested. Furthermore, if 1 mole of the electroneutral electrolyte to generate V plus and V negative moles of cations and anions in then equation 17 and 18, V plus into mu plus equals to V plus into mu naught plus V plus RT ln x plus V plus into RT ln f plus. This is equation 27. V minus into U minus equals to V minus into U naught minus plus V minus into RT ln x minus plus V minus into RT ln f minus, which is equation 28. To find the free energy change due to the per mole of cation and anion, add equation 27 and 28, then divide by V equals to V plus V minus. Then V plus into U plus V minus into U minus divided by V equals to V plus into U naught plus V negative into mu naught negative by V plus RT ln bracket start x plus to the power V plus and x minus to the power V negative to the whole power 1 by 2 plus RT ln bracket start f plus to the power V plus into f minus into the power V minus to the whole power 1 by 2, equation 29. Mu plus minus equals to V plus V plus V minus into mu minus divided by V, equation 30. Mu naught plus minus equals to V plus mu naught plus V minus into mu naught negative divided by V, equation 31. X plus minus equals to bracket start x plus power V plus into x minus power V minus to the whole power 1 by 2, equation 32. F plus minus equals to bracket start f plus power V plus f minus into the power V minus to the whole power 1 by 2, equation 33. Now using equation 32 33 in equation 29 we get mu plus minus equals to mu naught plus minus plus rt ln x plus minus plus rt ln f plus minus, equation 34. Taking logarithm both side of equation 33, ln f plus minus equals to 1 by v bracket start v plus ln f plus v negative ln f negative, equation 35. Now putting the value of ln f plus and ln f negative using equation 12, we get ln f plus minus equals to minus 1 by v bracket start na into e naught square into k divided by 2 e into r into t, again in numerator bracket start v plus into z plus square plus v negative into z minus square, equation 36. Now using the electron neutrality of the solution, v plus z plus must be equal to v negative z negative is v plus into z plus square plus v minus into z minus square equals to v plus into z plus into z negative plus v negative into z negative into z positive is equation 37. Next is v plus z plus square plus v negative into z negative square equals to z plus into z minus bracket start v plus v negative is equation 38. Next is v plus into z plus square plus v negative into z negative square equals to z plus into z negative into v equals to equation 39. After putting the value of equation 39 into equation 36, we have ln f plus minus equals to minus na into e naught square plus k divided by 2 into r into a into t. In numerator again we have z plus into z negative, which is equation 40. Furthermore, using the value of k using equation 21, the above equation takes the form ln f plus minus equals to minus na into e naught square into z plus into z negative divided by 2 into e into r into t bracket start 4 pi by e kt summation I ni naught into zi square into e naught square to the whole power 1 by 2, equation 41. Since ni naught equals to ci into ma divided by 1000, the equation 41 becomes ln f plus minus equals to minus na into e naught square into z plus into z negative divided by 2 into e into r into t bracket start 4 pi by e into k into t summation ci into na into zi square into e naught square divided by 1000 bracket closed to the whole power 1 by 2. This is equation 42. Multiply and divide the equation 42 by 2 and then put ci into zi square divided by 2 equals to I, that is ionic strength, we get ln f plus minus equals to minus na into e naught square into z plus into z negative divided by 2 into e into r into t bracket start 8 pi into na into e naught square divided by 1000 into a into k into t bracket close under root t, which is equation 43. Next, ln f plus minus equals to minus na into e naught square into z plus into z negative into b under root 1 divided by 2 into e into r into t equals to equation 44, where b is defined as b equals to bracket start 8 into pi into na into e naught square divided by 1000 into e into k into t to the whole power 1 by 2, equation 45. Converting the natural logarithm to the common algorithm, the equation 44 becomes log f plus minus equals to 1 minus 1 by 2.303 into na into e naught square into z plus into z minus divided by 2 into e into r into t into b under root 1, equation 46. After a new constant a as a equals to 1 by 2.303 into na into e naught square into b divided by 2 into e into r into t, equation 47. The equation 46 can be furthermore simplified as given below. Log f plus minus equals to minus a into z plus into z negative into under root 1, which is equation 48, which is Debye-Huckel limiting law of activity coefficients. Next topic is limitations of Debye-Huckel limiting law. The negative sign in the Debye-Huckel limiting law implies the fact that the activity coefficient is always less than unity. In order to discuss the limitation of this law, recall the popular relationship, that is log f plus minus equals to minus a into z plus into z negative into under root I, equation 1. Since a is a constant and the product z plus into z negative is also a constant for a particular electrolyte, the logarithm of activity coefficient must decrease linearly with the square root of ionic strength. In other words, the slope log f plus minus and root I can be determined simply by knowing the valencies of the ions involved and by the knowledge of some physical constant. Furthermore, it should also be noted that the slope is independent of the very nature of the electrolyte and is a function of valencies of cations and anions only. For instance, since the value of A for the water as a solvent is 0.509, the slope of for NaCl as well as for KCl must be equal to 1 into 0.509 only. For unibivalent and bivalent electrolyte, it should be 2 into 0.509 and 4 into 0.509. The logarithmic variation of mean ionic activity coefficient F plus minus with the square root of the ionic strength under root I for electrolytes of different valence follows the equation 1 pretty strictly. It is obvious from the both of the graphs that log f plus minus becomes 0 when the dilution is very large, indicating that the activity coefficient is unity, which is according to the Debye-Huckel limiting law. However, it should also be remembered that any theory is always a simplification of the real problem and therefore some deviations are expected. The same has been observed when the ionic strength is increased. It can be clearly seen that the deviation of the experimental result increases with the rise in the square root of the ionic strength. Next topic is Debye-Huckel-Onsager treatment for aqueous solutions and its limitation. It is a well-known fact that the conductance of weak electrolytic solution increases with the increase in dilution. This can be easily explained on the basis of Arrhenius' theory of electrolytic dissociation, which says that the magnitude of dissociated electrolyte and hence the number of charge carrier increases with the increase in dilution. However, the problem arises when the strong or true electrolytes show the same trend but at a much lower scale. We use the word problem because even at the higher concentration, the electrolyte dissociates completely, inferring that there is no possibility of further dissociation with dilution. This means that there should be no increase in the conductance of strong electrolytes with addition of water. The primary reason behind the weird behavior of strong electrolyte is that the conductance of only electrolytic solution depends not only upon the number of charge carriers but also upon the speed of these charge carriers. Therefore, if the dilution does not affect the number of charge carrier in strong electrolyte, it must be affecting the speed of ions to change its conductance. The main factor that is responsible for governing the ionic mobility is ion-ion interactions. Now, since these ion-ion interactions are dependent upon the interionic distances, they eventually vary with the population density of charge carriers. However, population density means smaller interionic distances and therefore stronger ion-ion interactions. On the other hand, the lesser population density of ions would result in larger interionic separations and hence weaker ionic interaction. In the case of weak electrolytes, the degree of dissociation is very small at high concentrations, yielding a very low population density of charge carriers. This would result in almost zero ion-ion interactions at high concentrations. Now, although the degree of dissociation increases with dilution, which in turn also increases the total number of charge carriers, the population density remains almost unchanged since extra water has been added for these extra ions. Thus, we conclude that there are no ion-ion interactions in weak electrolytes, neither at high nor at low concentration, and hence the rise in conductance with dilution almost a function dissociation only. In the case of strong electrolyte, the degree of dissociation is 100% even at higher concentration, yielding a very high population density of charge carriers. This would result in very strong ion-ion interactions at high concentration, hindering the speed of various charge carriers. Now, when more and more solvent is added, the total number of charge carrier remains the same, but the population density decreases continuously, creating large interionic separations. This would result in a decrease in ion-ion interaction with increasing dilution, and therefore the charge carriers would be freer to move in the solution. Thus, we can conclude that though there is no rise in the number of charge carriers with dilution, the declining magnitude of ion-ion interactions creates faster ions and larger conductance. Next topic is mathematical development of Debye-Huckel-Onsager theory of strong electrolytes. It is a well-known fact that the equivalent conductivity of an electrolytic solution is correlated to the ionic mobilities mu ions involved as lambda equals to F into mu plus mu negative, equation 1, where F is the Faraday constant. Now recall the ionic mobilities of cation and anion, that is mu plus equals to mu naught plus minus K into Z plus into E naught divided by 6 pi n plus E naught square into omega divided by 6 into E into K into T into mu naught plus, equation 2. Next is mu negative equals to mu naught negative minus K into Z negative into mu naught divided by 6 pi n plus mu naught square into omega into mu naught negative divided by 6 into A into K into T, equation 3, where mu naught plus and mu naught negative are the ionic mobilities of the cation and anions at infinite dilution respectively. The symbol E represents the dielectric constant of the medium, whereas N is the coefficient of viscosity. Z plus and Z negative are the charge numbers of the cation and anion respectively. The symbol E naught simply shows the electronic charge. The symbol K represents N naught I is the bulk concentration. Next, K equals to 4 bracket start 4 pi divided by E into K into T summation I n naught I into Zi square into E naught square to the whole power 1 by 2 equals to bracket start 4 pi Z square E naught square into C divided by E into K into T to the whole power 1 by 2 into again bracket start Na divided by 1000 to the whole power 1 by 2, equation 4. The quantity omega is defined as W equals to Z plus into Z negative into 2Q divided by 1 plus under root Q, where Q equals to Z plus into Z negative divided by Z plus Z negative, again lambda plus lambda negative divided by Z plus into lambda plus Z negative into lambda negative, equation 5. After putting the values of mu plus and mu negative from equation 2 and 3 in equation 1, we get lambda equals to F into mu naught plus minus K bracket start Z plus into E naught divided by 6 into pi into n plus mu naught square into omega into mu naught plus divided by 6 into E into K into T bracket close plus F again bracket start mu naught negative minus K again bracket start Z minus E naught divided by 6 pi n plus mu naught square into omega divided by 6 E K T bracket close mu naught negative, equation 6. In the case of symmetrical electrolytes, we can put Z plus equals to Z negative equals to Z, and therefore Z plus Z negative equals to 2Z. Thus the above equation for such cases takes the form lambda equals to F into mu naught plus mu naught negative minus bracket start F into Z into K into E naught divided by 3 pi n plus E naught square into omega into K into F into mu naught plus mu naught negative divided by 6 into E kt, equation 7. Since f into mu naught plus mu naught negative equals to lambda naught, the equation 7 becomes lambda equals to lambda naught minus bracket start f j z k e naught divided by 3 pi n plus e naught square plus w into k into lambda naught divided by 6 e kt, equation 8. Now expanding above equation further by putting the value of k from equation 4, we get lambda equals to lambda naught minus bracket start f into z into e naught divided by 3 pi n, again bracket start 8 pi z square e naught square na divided by 1000 e kt to the whole power 1 by 2 plus e naught square into omega divided by 6 e kt bracket start 8 pi z square into e naught square into na divided by 1000 e kt to the whole power 1 by 2, then multiply lambda naught bracket close under root c. This is equation 9. Define two constants a and b as a equals to f z e naught divided by 3 pi n bracket start 8 pi z square e naught square into na divided by 1000 e kt to the whole power 1 by 2. Next, b equals to e naught square into omega divided by 6 e kt to the bracket start again 8 pi z square into e naught square into na divided by 1000 e kt to the whole power 1 by 2. Both these are equation 10. Therefore, the equation 9 can be simplified as lambda equals to lambda naught minus a plus b into lambda naught bracket close under root c. This is equation 11. Or we can say that lambda equals to lambda naught minus constant into under root c, equation 12. The equation 9 and equation 11 are the popular famous Debye-Huckel-Onsager equation for the electrolytic solution. The constant A and B can be easily determined from the knowledge of temperature, valence type of electrolyte Z, the viscosity of medium, the dielectric constant and other universal constant like Avogadro number. From equation 12, it is obviously a straight line equation, which means that for symmetrical electrolyte solution, we can plot the conductance versus square root of the concentration, for which the slope will be negative. The intercept after extrapolation gives the value of conductance of such solutions at infinite dilution. Next topic is limitations of Debye-Huckel-Onsager equation. Since the plot of conductance versus square root of the concentration is linear with negative slope and the positive intercept, it seems quite straightforward to study the strong electrolytes. However, it has been observed that the equation 12 is followed only up low and moderate concentration. It can be clearly seen that the theory and experiment move apart as the concentration increases. This is simply because some approximation used to derive our Debye-Huckel-Onsager equation are not valid. Next topic is Debye-Huckel-Onsager theory for non-aqueous solution. Before we discuss the Debye-Huckel-Onsager theory for non-aqueous solutions, recall the same for aqueous solution, that is lambda equals to lambda naught minus constant under root c, equation 12, or we can say that lambda equals to lambda naught minus a plus b lambda naught into under root c, equation 13, where the two constant a and b were defined as a equals to f z e naught divided by 3 pi n bracket start 8 pi z square e naught square into na divided by 1000 e kt to the whole power 1 by 2, equation 14, and b equals to e naught square into omega divided by 6 e kt bracket start 8 pi z square e naught square into na divided by 1000 e kt to the whole power 1 by 2, equation 15, where f is the Faraday constant, na is Avogadro number, the symbol e represents the dielectric constant of the medium, whereas n is the coefficient of viscosity. Z is the charge of number of cations and anion. The symbol E naught simply shows the electronic charge. The quantity W is defined as W equals to Z plus into Z negative into 2Q divided by 1 plus under root Q, where Q is defined as Q equals to Z plus into Z negative divided by Z plus Z negative. Again in numerator lambda plus lambda negative divided by z plus into lambda plus z negative into lambda negative. It is obvious from the Debye-Huckel-Onsager equation that the plot of conductance versus square root of concentration will be a straight line with a negative slope and positive intercept. The intercept after extrapolation gives the value of conductance of such solutions at infinite dilution. Now it has been observed that the Debye-Huckel-Onsager equation can also be applied to non-aqueous solutions up to the fairly good agreement. For instance, consider the variation of equivalent conductivity as a function of square root of the concentration of different alkali sulfocyanates in the methanol as the solvent. The theoretical predictions show that the results of the Debye-Onsager equation are in good agreement with the experiment up to 0.002 mole per decimeter cube. In going from water to non-aqueous solvent, a significant variation in the quantities like dielectric constant of the medium, the distance of the closest approach, or viscosity is observed. Now, since the Debye-Onsager equation does have these quantities, the slope and intercept of the lambda versus c to the power 1 by 2 may also vary drastically. Next topic is the solvent effect on the mobility at infinite dilution. As we know that the asymmetry and electrophoretic effects are not active at infinite dilution because of their dependence on the size of ionic clouds. The mobility of ions in such cases can be formulated simply from the Stokes law, that is mu naught concentration equals to Z into E naught divided by 6 pi nr. This is equation 16, where r represents the radius of the solvated ion and n is the coefficient of viscosity, z is the charge number of cation and anion, and symbol E naught simply shows the electronic charge. Now, if we imagine the same electrolyte in different electrolytic solution, we can say mu naught concentration into n into r equals to constant. This is equation 17. Assuming further that the r is always also independent of solvent type, we have mu naught concentration into n equals to constant. This is equation 18. It is obvious from the equation 18 that ionic mobility is inversely proportional to the coefficient of viscosity. More viscous solvents would result in a slow drift of ions and vice versa. It has also been found that the equation 18 is more valid for solvents other than water. Moreover, the radius of solvated ion may vary drastically in going from one solvent to another. In some cases, it gets even double. The result of equation 18 does not find a very large application domain. This variation in the solvated radius is primarily due to the difference in the size of the solvent molecules. For instance, the size of the solvated ion is larger in ethanol than in methanol, which in turn is larger than what is observed in water. All this results in an opposite trend in the ionic mobilities and therefore in the equivalent conductivities as well. Recalling the simple Walden's rule, that is lambda n equals to constant, this is equation 19, where lambda is the equivalent conductivity of the electrolytic solution at concentration C. This simply means that the equivalent conductivity and the viscosity of the solvent are inversely proportional to each other. However, the effect of the solvated radius must be considered for more accurate results. Therefore, we must more acceptable form of Walden's rule, that is mu naught nr equals to constant. This is equation 20. The symbol r represents the radius of the ionic species considered in the solvent under examination. Next topic is modification of Debye-Huckel limiting law for finite size ions. Debye-Huckel limiting law can be modified for finite size ions by adding a term to the equation that accounts for the ion size, often called as the extended Debye-Huckel equation. This modification involves using the ion's effective hydrated radius A in the formula, which corrects the activity coefficient for ion-ion and ion-solvent interaction that are significant at higher concentration where the limiting law breaks down. Modified equation, the extended Debye-Huckel equation, is typically written as log gamma plus minus equals to minus A modulus Z plus into Z negative into under root I divided by 1 plus dA into under root I. Ion size term. The key modification is the addition of the term 1 plus dA into under root I in the denominator. A represents the effective diameter of the ion, which includes the ion and its associated tightly bound water molecules, hydrated radius. B is a constant that depends on temperature and solvent properties. Next topic is effect on ion-solvent interaction on activity coefficient. Ion-solvent interactions such as ion dipole forces and hydration significantly affect the activity coefficient by influencing how ion behaves in solution, causing deviations from ideal behavior. These interactions along with ion-ion interaction determine the non-ideal nature of the solution, which is captured by the activity coefficient, a factor that modifies the concentration to reflect thermodynamic reality. Next is influence of Influence on thermodynamic properties. Ion-solvent interaction contribute to the overall non-ideality of a solution. The activity coefficient Fi is a measure of this deviation from ideal behavior, where Fi would be 1 for an ideal solution. Next is contribution to chemical potential. Ion-solvent interactions are a fundamental part of the chemical potential of ions in a solution, which is then used to derive activity coefficient. Next is model components. Theoretical models like mean spherical approximation explicitly include both ion-ion and ion-solvent interaction terms to calculate the electrostatic contributions to the chemical potential and activity coefficients of the electrolyte solution. Next topic is physical significance of activity coefficient. First is measures non-ideal behavior. Electrolytic solutions are often far from ideal even at low concentration due to the ionic atmosphere of surrounding ions. Activity coefficient gamma are used to modify concentrations m so that thermodynamic relations like the chemical potential equation mu I equals to mu naught I plus RT ln AI remain valid for ideal solutions. Next is reflects the interaction. They account for the electrostatic interaction between ions which are not accounted for in ideal solution theory. For example, an ion's chemical potential is affected by the net electrical potential created by the surrounding ions. Next is quantifies effective concentration. Activity is often defined as the product of concentration and activity coefficient, that is AI equals to gamma I star into Mi. The activity AI is the effective concentration that correctly predicts thermodynamic properties like equilibrium constant and reaction rate. Next is allows for the thermodynamic calculation. By using activity coefficient, it is possible to apply thermodynamic laws and equations developed for ideal systems to real and non-ideal electrolytic solutions. This is crucial for accurately predicting electrochemical potential, solubilities and reaction equilibria. Next topic is effect of ion association upon conductivity, Debye-Huckel-Bejerome equation. According to Debye-Huckel theory of ion-ion interaction, the ions produced by the dissociation of electrolytes are randomly distributed in the solution with oppositely charged ionic clouds surrounding them. Nevertheless, the possibility that some negative ions might get very close to the positively charged reference ion was neglected. In such a situation, the translation thermal energy would not be enough to make the ions to move independently and an ionic pair may be formed. Being a combined entity of two equal and opposite charges, these ion pairs are completely neutral and distributed randomly in the electrolytic solution. These neutral ion pairs are not influenced by the reference ion under consideration. Therefore, the fraction of ions participating in these ion pairs must be obtained for a more accurate picture of the electrochemical property of the solution. In order to understand the concept, imagine a spherical shell at a distance r from the reference ion with dr thickness. The probability of finding the anion Pr in the spherical shell is proportional to three main factors. The first one is the ratio 4 pi r square dr, volume element to the total volume V. The second one is the total number of anions, that is n negative, and the third is e to the power minus u by kt. U represents the potential energy of anions situated at distance r. Mathematically, we can formulate this as Pr equals to bracket 4 pi r square dr by V into n negative into e to the power minus u by kt, equation 202. Now, because n negative by V represents the anions concentration n not negative, the above equation takes the form Pr equals to 4 pi r square dr into n not negative into e to the power minus u by kt. This is equation 203. Furthermore, after recalling the value of u, that is u equals to minus z plus into z negative into e naught square divided by er, equation 204. Equation 203 becomes Pr equals to 4 pi r square into n naught negative into e to the power z plus into z negative into e naught square divided by e t kt into dr, equation 205, where E is the dielectric constant of the medium and E naught is the electronic charge. Now define a new parameter lambda as lambda equals to z plus into z negative into E naught square divided by E kt, equation 206. Therefore, we can write Pr equals to 4 pi n naught negative into e to the power lambda by r into r square into dr, equation 207. Similarly, the probability of finding a positively charged ion at a distance r in dr thickness around a negatively charged reference ion will be Pr equals to 4 pi n plus n naught plus into e to the power lambda by r into r square into dr, equation 208. Therefore, the probability of finding ith type of ion at a distance r in dr thickness around a kth type of reference ion can be formulated as Pr equals to 4 pi n plus naught into e to the power lambda by r into r square into dr, equation 208, where lambda equals to zi into zk into e naught square divided by ekt, equation 209. The variation of probability of finding one type of ion around other types shows a strange behavior with distance. Where r varies from a very small to moderate value, the magnitude of Pr decreases because the factor e to the power lambda by r. However, after a certain value, the probability starts to rise due to dominance of the directly correlated factor of r square. Hence, we can say that the probability of finding the oppositely charged ion at distance r from the reference ion first decreases and then increases as we move away from the central ion. Since the probability of finding a negative ion within a certain distance around a positive ion is obtained by applying the lower and upper bounds, we need to find these limits first. Now, because ion pair can be formed only if the participating ion close enough so that the electrostatic attraction can outshine the thermal forces, let this distance be represented by theta. In other words, we can say that the formal formation of ion pair takes place only if the separation between the cation and anions is less than q. Since the cation and anion cannot approach each other closer than the ionic size parameter A, that is distance of closest approach, the ion pair will be formed for an interionic separation of greater A but less than Q. The probability of the ion pair formation is the number of ith type of ion participating in the ion association to the total number of the same type of ions. Therefore, the probability of ion pair formation theta can be formulated as theta is equals to integration a to q pr dr, which is equals to integration sign a limit a to q 4 pi ni naught into e to the power lambda by r into r square into dr, equation 210. Owing to the divergent nature of the integral, the upper limit can be set to the overall probability minima q as shown below. To find the minima, differentiate equation 208 with respect to k with respect to r and then put equal to 0, that is dpr by dr equals to 4 pi n naught I into e to the power lambda by r 2r plus 4 pi n naught I into r square e to the power lambda by r into lambda by r square, equation 211. Next, 2r minimum minus lambda equals to 0, this is equation 212. Or we can say that q equals to r minimum, which is equals to lambda by 2, this is equation 213. After putting the value of lambda from equation 206 into 213, we get q equals to z plus into z negative into e naught square divided by 2 e kt. This is equation 14. Bejorum claimed that only Coulombic interactions short range leads to the formation of ion pairs, and if the separation of cation and anion larger than q, they should be treated as free ions. In other words, we can say that the formation of ion pair is feasible if A is less than Q and infeasible if A is greater than Q. Using the upper limit as Q equals to lambda by 2, the probability of ion pair formation theta becomes theta equals to 4 pi n naught I integration limit A to lambda by 2 e to the power lambda by r into r square into dr, equation 215. At this stage, after define a new variable for simplicity, gamma equals to lambda by r equals to 2q by r and a new constant b equals to lambda by a. The above equation takes the form theta equals to 4 pi ni naught into z plus into z negative e naught square divided by e kt to the whole power 3. Integration limit z to gamma e to the power gamma into y into dy, equation 216. Hence, using the above equation, we can easily determine the fraction of ions reserved in pairing and cannot move freely. Nevertheless, it would be more beneficial if we could use some simple number to quantify the magnitude of ion pair formation instead of theta. From the Arrhenius theory of electrolytic dissociation, we know that A plus B minus type electrolyte would give monovalent cations and anions in water, that is AB equals to A plus B negative, to equation 217. Using the law of mass action, the dissociation constant can be given as K equals to A to the base A plus A negative to the base B divided by A to the base AB, equation 218. Similarly, if a cation M plus and anion A negative form an ion pair, that is M plus A negative equals to IP, the law of mass action can also be used to give association constant as Ka equals to AIP divided by AM plus A negative, equation 220, where AM plus and A negative and AIP are the activities of the cation, anion and ion pair respectively. Moreover, it can also be seen that the association constant is just the reciprocal dissociation constant. Now theta is the fraction of the ions forming ion pair, where theta c and 1 minus theta c are the concentration of ion pair and free ions respectively. Therefore, the association constant in terms of activity coefficient can be written as Ka equals to Qc into Fip divided by 1 minus theta into Cf plus into 1 minus theta into Cf negative, equation 221. Or we can say that Ka equals to Q divided by 1 minus Q square into 1 by C into Fip divided by F plus into F negative, equation 222. F plus, F negative and Fip are the activity coefficient for cation, anion and ion pair respectively. In terms of mean ionic activity coefficient and analytical concentration, the equation 222 can also be written as Ka equals to theta divided by 1 minus theta square into 1 by Ca into Fip divided by F plus minus square, equation 223. Now, because the ion pairs are neutral species and therefore do not participate in ion-ion interactions, the activity coefficient ion pairs can be taken as unity. Therefore, equation 223 can be written as Ka equals to theta by 1 minus theta square into 1 by Ca into 1 by F plus minus square, equation 224. Or theta equals to Ka into 1 minus theta square into Ca into F plus minus square, equation 225. At this stage, the only thing that is needed for further treatment is the relation between theta and the conductivity of the electrolyte used. To do so, recall the correlation between the concentration of free ions and specific conductivity sigma, that is sigma equals to Zf into U plus U negative into C free ions, 226, where F is Faraday constant. Sigma is equals to Z into F into mu plus mu negative into C free ions into Ca divided by Ca, equation 227. The term C free ions by Ca is the fraction of ions that are free, not associated, and therefore C free ions by Ca equals to 1 minus theta, equation 228. Using the result of equation 228 in equation 227, we get sigma equals to Zf mu plus mu negative into 1 minus theta into Ca, 229. Furthermore, after converting the specific conductivity to equivalent conductivity, lambda equals to sigma by Z into Ca, the equation 229 takes the form lambda equals to F into mu plus mu negative into 1 minus theta, equation 230. Imagine a situation if no ion association occurs, theta equals to 0, then the equation 230 would reduce to lambda theta equals to 0, which is equals to F into mu plus mu negative, equation 231. Using equation 231 in equation 230, we get lambda equals to lambda theta equals to 0 into 1 minus theta, equation 232. Or we can say that lambda by lambda theta equals to 0 equals to 1 minus theta, equation 233. Or we can say that theta equals to 1 minus lambda by lambda theta equals to 0 equation 234. Now putting the values of theta and 1 minus theta from equation 234 and 233 in equation 225, we have 1 minus lambda by lambda theta equals to 0 equals to ka into a by lambda theta equals to 0 to the whole square into ca into f plus minus square, equation 235. Rearranging, we get 1 minus 1 by lambda equals to 1 by lambda theta equals to 0 plus ka into f plus minus square into lambda into ca divided by lambda theta equals to 0 square, equation 236. Rearranging equation 229 for f into mu plus mu negative and putting in equation 231, we get lambda theta equals to 0 equals to f into mu plus mu negative equals to sigma by z into 1 minus theta into ca, equation 237. The above equation shows equivalent conductivity at zero ion association at 1 minus theta into Ca concentration. Therefore, we must use Debye-Huckel-Onsager equation to express the more appropriate conductivity at small concentration. That is, lambda theta equals to 0 equals to lambda naught minus a plus b into lambda naught into under root 1 minus theta into under root Ca, equation 238, where the two constants a and b are defined as a equals to f z e naught divided by 3 pi n bracket start 8 pi z square e naught square na divided by 1000 e k t to the whole power 1 by 2 and b equals to e naught square into omega divided by 6 e k t bracket start 8 pi z square e naught square na divided by 1000 e k t to the whole power 1 by 2, equation 239, where f is the Faraday constant and na is the Avogadro number. The symbol E represents the dielectric constant of the medium, whereas n is the coefficient of viscosity, z is the charge number of anion, and symbol E naught simply shows the electronic charge. Omega is the parameter defined earlier in this chapter. The equation 238 can be simplified as lambda theta equals to 0 equals to lambda naught omega, equation 240, where w represents a continued fraction, that is w equals to 1 minus w bracket start 1 minus w again bracket 1 minus w minus to the power of minus 1 by 2 again bracket close to the power minus 1 by 2 bracket close power 1 minus 1 by 2, equation 241, provided that w equals to a plus b lambda naught into under root ca into under root lambda divided by lambda square to the whole power 1 by 2, equation 242. Using the result of equation 240 and equation 236, we get 1 by lambda equals to 1 by lambda naught into w plus ka into f plus minus square divided by lambda naught omega to the whole square into lambda ca, equation 243, or w by lambda equals to w by lambda naught plus ka into f plus minus square plus lambda ca divided by lambda naught square into omega, equation 244. After looking at the above equation, it is obvious that the formation of ion pairs has changed the variation of equivalent conductivity with concentration drastically. When the formation of ion pairs are ignored, the variation of equivalent conductivity with concentration was empirically explained by the Kohlrausch law. Nevertheless, in the case of non-aqueous solvents, the dielectric constant, a significant amount of ion pair formation occurs, and therefore W by lambda is plotted versus F plus minus square lambda Ca by W, with W by lambda naught as intercept and Ka by lambda naught square as slope. Next topic is Debye-Huckel theory of ion-ion interaction. When an ion goes into solution, it interacts not only with the solvent molecule but also with other ions that are produced as a result of electrolytic dissociation. The interaction of this ion with its solvent surrounding is quite important as it helps ion to get stabilized in that medium. Nevertheless, the other types of interaction, that is the ion-ion interaction, are also of very much significant values to the overall understanding of the system, because these interactions affect a number of properties of these solutions, such as partial molar free energy charge or the electrolytic conductance. Now, since the phenomena of ion-ion interaction is a function of interionic separation, which in turn depends upon the population density of these ions, the first step to know the phenomena must be rationalization of ionic population density. In the case of weak electrolyte, the degree of dissociation is very small at high concentration, yielding a very low population density of charge carriers, This would result in almost zero ion-ion interactions at high concentrations. Now, although the degree of dissociation increases with dilution, which in turn also increases the total number of charge carriers, the population density remains almost unchanged since the extra water has also been added for these extra ions. Thus, we can conclude that there are no ion-ion interaction in weak electrolytes, neither at higher nor at the lower concentration. On the other hand, in case of strong electrolyte, the degree of dissociation is 100% even at high concentration, yielding a very high population density of charge carriers. This would result in very strong ion-ion interaction at high concentration. Now, when more and more solvent is added, the total number of charge carriers remains the same, but the population density decreases continuously, creating large interionic separations. This would result in a decrease in magnitude of ion-ion interaction with increasing dilution. In 1913, a British physicist, Samuel Milner, proposed the first quantitative explanation of ion-ion interaction in a statistical framework. After that, in 1918, an Indian chemist, Sir Janan Chandra Ghosh, proposed a model to compute the energy of Coulombic interaction of the ions with an assumption that the ionic ions in the solution are fixed just like in the crystals. The Milner models was quite complicated mathematically, while Gauss model did not consider the distorting effect of thermal motion of the ionic distribution in the solution phase of the electrolyte under consideration. In 1923, Peter Debye and Heinrich Haeckel proposed an extremely important idea to quantify the ion-ion interaction in the solution of strong electrolyte. In this model, the solute, that is the strong electrolyte, is assumed to dissociate completely. They considered the ions as perfect sphere that cannot be polarized by the surrounding electric field, while the solvation of ions was ignored. The solvent plays no role other than providing a medium of the constant relative permittivity dielectric constant. A reference ion was thought to be suspended in the solvent continuum of dielectric constant E with zero electrorestriction, and this ion is surrounded by oppositely charged ionic cloud. Fundamental concept. It is quite interesting to recall the fact that, like many other coupling effects, the phenomena of ion-ion interaction can also be quantified in terms of free energy change. In this case, it can be achieved by assuming an initial state with no ion-ion interaction and a final stage in which the ion-ion interaction do exist, and then calculating the free energy change in going from initial to final state. The initial state, that is the state with no ion-ion interaction, can be created hypothetically by taking ions in the vacuum. However, since the final state possesses ions in solution, the initial state should also have ions in solution and not in vacuum. Otherwise, two states would differ not only by ion-ion interaction but also in respect of ion-solvent interaction. Conversely, if we imagine some discharged ions in the solution, discharged ions means no ion-ion interaction, and then charge them up fully, then energy change of ion-ion interaction would be the amount of work done in doing so. It should also be noted that the procedure depicted gives the work of charging, that is the free energy of ion-ion interaction, for all the ions present in the solution, whether they are positive or negative. However, the scientific analysis of electrolytic solution typically needs the free energy of ionic interaction for individual species. This partial free energy change is also called as chemical potential change and is typically for individual species. The partial free energy change is called as chemical potential change and is typically denoted as lambda mu I minus I. The value of lambda mu I minus I for ith species of radius Ri can be obtained by computing the work of charging the sphere from a neutral state to its full charge of Ze0. The work of charging W is a spherical conductor can be given in the following relation from electrostatics. W equals to 1 by 2 into charge on the conductor into electrostatic potential of conductor, equation 1. Since the Debye-Haeckel model also considers the ions as a spherical conductors, the work on charging an ion of the radius R will be W equals to 1 by 2 into Zie0 into psi, equation 2, where psi represents the electrostatic potential of the reference ion due to the influence on it by the Coulombic forces of the neighboring ions. Multiplying equation 2 by Avogadro number, we can obtain the amount of work done required to charge 1 mole of such ions, that is partial molar free energy change. Lambda delta mu I minus I equals to Na into W, which is equals to Na divided by 2 into zi e naught into psi, equation 3. The only thing that is unknown in the above expression is psi. Therefore, the partial molar free energy change due to the interaction of ith species with the rest of the solution requires the determination of electrostatic potential exerted at the reference ion by its ionic surrounding. Now, from the law of suspension of potential, we know that the potential at any point due to assembly of charges is just the sum of individual potential exerted at that point by the individual charges. Since the electrostatic potentials depend upon the distances between the charges under consideration, the time average distribution of all the ions around must be known. Distance from the reference ion are the function of the population distribution of other ions. Although we know that the total electrostatic potential at the reference ion can be obtained by knowing the distance of each surrounding ion from the reference ion, the number of ions is extremely large, making it almost impossible to follow the conventional route to do so. So instead of dealing with individual ions, Debye and Huckel proposed the revolutionary idea of considering all the surrounding ions as a continuous ionic cloud that surrounding the reference ion. They assigned the discrete charge only to the reference ion, which is situated in the solvent's continuum of dielectric constant. Hence, the Debye-Huckel idea transformed the complex problem of computing the population density around the reference to the determination of excess charge density delta. At this point, one might think why the excess charge density is not zero everywhere, because the solution as a whole is actually electroneutral. The reason for this behavior lies in the fact that the positive center attracts negative density while a negative center tries to accumulate a positive cloud around it. Therefore, in a volume element near positive ion there should be a more negative charge, that is excess negative charge density, and vice versa. This excess negative charge density near a positive center is counterbalanced by excess positive charge density near a negative center, keeping the overall electron neutrality maintained. It should also be mentioned here that since the thermal forces in the solution are always trying to randomize the ionic distribution, the excess charge density diminishes in moving away from the center. Next is mathematical development. So far, we have discussed the fundamental aspect of how we determine the partial molar free energy change generated by the ionic interaction of the ith species. All we need the electrostatic potential psi of the reference ion due to the influence on it by the Coulombic force of the surrounding. Since psi at a distance r from the reference ion depends upon the excess charge density, the first thing we need to develop is mathematical is the correlation between the two parameters, that is psi and pr. One such relation for spherically symmetric charge distribution is the Poisson's equation in electrostatic, that can be given as I by r square into d by dr into r square into d psi r by dr equals to minus 4 pi into pr divided by e, equation 4, where psi r and pr are the electrostatic potential and excess charge density in a very small volume element dv situated at a distance dr from the reference ion. Rearranging the Poisson's equation for excess charge density, we get Pr equals to minus E by 4 pi bracket start 1 by r square d by dr into r square into d into psi r divided by dr, equation 5. Also, the linearized Boltzmann distribution can be used to prove that Pr equals to minus summation I n naught I into zi square into e naught square into psi r by kt, equation 6, where ni naught is the bulk concentration of the ith species and k is simply Boltzmann constant. Equating the Poisson's expression with Boltzmann formula, that is from equation 5 and 6, we get the linearized Poisson Boltzmann equation as minus e by 4r into 1 by r square into d by dr into r square into d psi r divided by dr equals to minus summation I n naught I into zi square into e naught square into psi r divided by kt, equation 7. Or we can say that 1 by r square into d by dr into r square into d into psi r divided by dr equals to 4 pi by e kt summation I n naught I into z I square into e naught square into psi r, equation 8. Now assume a constant k square with the value k square equals to 4 r divided by 4 pi divided by e kt summation I n naught I into zi square into e naught square, equation 9. Using the value of equation 9 in equation 8, we get 1 by r square into d by dr into r square into d psi r divided by dr equals to k square into psi r, equation 10. The above differential equation is the popular form of the linearized Poisson-Boltzmann expression, and its solution gives psi r equals to zi into e naught into e to the power minus kt divided by e into r, equation 11. Now comparing equation 4 and equation 10, we get k square psi r equals to minus 4 pi by e into pr, equation 12. Pr equals to minus e k square into psi r divided by 4 pi, equation 13. Now putting the value of electrostatic potential from equation 11 in equation 13, we get the expression for the excess charge density as a function of r. Pr equals to minus e k square divided by 4 pi into zi into e naught into e to the power minus kr divided by e into r, equation 14. Pr equals to minus zi into e naught into k square into e to the power minus kt divided by 4 pi r, equation 15. Now because of the magnitude of Pr is a consequence of the unequal distribution of anion and cation, the above expression also defines the ionic population distribution around the reference ion. After knowing that the excess charge density decreases exponentially with r, we can determine the total excess charge dq at the same distance just as the following relation. dq is equals to pr into 4 pi r square dr, equation 16, where 4 pi r square dr is the volume element of a hollow spherical shell of thickness dr with the inner and outer radius as r and r plus dr respectively. After putting the value of pr from equation 15 in equation 16, we have dq is equals to minus zi e naught k square into e to the power minus kr divided by 4 pi r into 4 pi r square dr, equation 17. dq equals to minus zi into e naught into e to the power minus kt into k square r dr, equation 18. Thus the exponential part decreases with increasing r, while the non-exponential part shows a continuous increase as we move away from the reference ion. In order to find the distance of maximum excess charge, we need to differentiate the equation 18 with respect to r, and then derivative needs to be put equals to 0. dq by dr equals to minus zi e naught k square into e to the power minus kr e to the power minus kr equals to 0, equation 19. Since minus zi e naught k square is non-zero for sure, the above equation holds true only if e to the power minus kt equals to k r e to the power minus k r equals to 0, equation 20, which implies r equals to k to the power minus 1, equation 21. Also from the equation 9, we have k equals to 4 pi by e kt summation n naught I into zi square into e naught square to the whole power 1 by 2, equation 22. Hence the radius of maximum excess charge from the center of the reference ion can be obtained by putting the value of k from equation 22 in equation 21. We get r max, or the de Broglie length, as r max is equals to ekt divided by 4 pi into 1 by summation I n naught I into zi square into e naught square to the whole power 1 by 2, equation 23. At this point we have understood most of the ideas of de Broglie theory of ion-ion interaction, and the question we raised initially is near to its end, that is to calculate the molar chemical potential change of ion-ion interaction. Now, although we have calculated the electrostatic potential, we cannot use the same in equation 3, because what we have obtained contains the contribution from the ionic cloud as well as from the reference ion itself. Therefore, before we calculate the partial molar free energy of ion-ion interaction, we need to separate potential from the ionic clouds and from the central ion first. The total electrostatic potential at a distance r can be fragmented as given below. Psi r equals to psi ion plus psi cloud, equation 24. Psi cloud equals to psi r minus psi ion, equation 25. From the formulation of potential due to a single charge at a distance r, we know that psi ion equals to zi into e naught by e r, equation 26. Now using the value of psi r from equation 11 and psi m from equation 26 into equation 25, we get psi cloud equals to zi e naught e to the power minus k r divided by ER minus ZI E naught divided by ER, equation 27. Psi cloud equals to ZI E naught into e to the power minus KR minus 1 divided by ER, equation 28. Now because the value of K is proportional to summation N naught I ZI square E naught square at a very large dilution, K becomes very small and e to the power minus KR can be expanded as 1 minus KR into e to the square equals to 1 plus x. Therefore, equation 28 takes the form psi cloud equals to zi e naught into 1 minus kt minus 1 divided by er, equation 29. Psi cloud equals to minus zi into e naught into k by e, equation 30. Hence, the potential due to the ionic cloud is independent of the distance r in this case. Now, putting the value of psi cloud from equation 13 into equation 3, we get del ui minus I equals to NaW equals to Na by 2 into Zi E naught into minus Zi into E naught into K by E, equation 31. Del ui minus I equals to minus Na into Zi square into E naught square into K by 2E, equation 32. Hence, the Debye-Huckel model gives the theoretical value of del ui minus I arising from ionic interaction. Now, before we check the validity of Debye-Huckel model, we will discuss many aspects of mathematical treatment of Debye-Huckel model in more detail in forthcoming sections. Next topic is activity coefficient of electrolyte. Activity coefficient, consider the dissociation of a univalent electrolyte represented as Ma equals to in equilibrium M plus A negative. Applying the law of chemical equilibrium, we have K equals to A M plus into A negative divided by A Ma, equation 33. The activity is related to concentration expressed in terms of molality, that is in terms of moles per kg of the solvent by expression A equals to lambda m, where lambda is the activity coefficient. Thus K equals to lambda m plus into m plus into lambda A minus into Ma minus divided by lambda Ma into Ma, which is equals to lambda m plus into lambda A negative divided by lambda Ma into m to the base m plus Ma negative divided by Ma, equation 35. Mean activity coefficient. It is not possible to have only one kind of ions in the solution. If there are anions, there have to be cations as well, so that the total positive charge is equal to the total negative charge in the solution, which is evidently neutral. The question of determining activity or activity coefficient of individual ions therefore does not arise. New terms such as mean ionic activity or mean ionic activity coefficient therefore need to be introduced. Consider ionization of a univalent electrolyte Ma, where Ma gives Ma plus and A negative. The activity of the cation may be denoted by A plus and that of the anion be denoted as A negative. Both the quantities are indeterminable, since it is not possible to have ions exclusively of one charge present in a solution. Hence, mean ionic activity of the electrolyte has to be taken into consideration. The activity and the mean ionic activity of the electrolyte denoted by A and A plus minus respectively are defined by the expression A equals to A plus into A negative equals to A plus minus square, equation 36. For any other electrolyte of the type MXAY, which ionizes as MXAY in equilibrium, gives X into M plus Y into A negative. The activity and mean ionic activity will be given by A equals to AX to the A plus to the power X into A negative to the power Y, which is equals to A plus minus A to power X plus Y. For the sake of simplicity, the charge on each cation is represented by a single plus, on each anion by a single minus. If M is the initial concentration of electrolyte Mx into Ay in terms of moles per 1000 gram of the solvent, the concentration M plus and A negative ions would be Xm and Ym moles per 1000 gram of the solvent respectively. Knowing that the activity is related to molar concentration molality by the expression A equals to lambda into M, equation 37 may be represented as A equals to X into lambda plus M to the power X into Y into lambda negative into M into to the power Y, equation 38, equals to X to the power x into y to the power x into lambda plus to the power x into m to the power x plus y equals to x to the power x y to the power y into lambda plus minus into m to the whole power x plus y. Equation 39, where lambda plus minus is the mean molar ionic activity coefficient or simply mean activity coefficient of the electrolyte. It is evidently defined as lambda plus minus to the power x plus y equals to lambda plus to the power x into lambda minus into the power y. Equation 40. Thus, if A is determined experimentally, it is possible to calculate the mean activity coefficient by applying equation 40. The values of x and y depend on the nature of electrolyte. In case of univalent electrolyte KCl, x is equals to 1 and y equals to 1. Equation 39 may therefore be written as A equals to lambda plus minus into m to the whole square. Equation 41. For a bivalent electrolyte K2SO4, x is equals to 2 and y equals to 1. Equation 39 therefore takes the form A equals to 2 square into 1 to the power 1 into lambda plus minus into m to the whole power 2 plus 1. Equation 42, which is equals to 4 into lambda plus minus cube into m cube. The activity coefficient of each electrolyte at infinite dilution is taken as unity. Mean activity ionic coefficient of various electrolytes at different concentration molarities can be calculated from equation 40. The value of activities are usually determined by EMF, freezing point depression and vapor pressure lowering method. It is seen at a lower concentration, the mean ionic activity coefficient is close to unity, that is, the departure from ideal behavior is small. But as concentration increases, the activity coefficient falls much below unity and approaches a certain minimum value, indicating much larger departures from the ideal behavior. As concentration rises further, the mean ionic activity coefficient start increasing and in some cases even exceeds unity, that is, activity becomes greater than concentration. This behavior is shown more clearly in this figure, in which mean activity coefficient of some of the electrolytes have been plotted against square root of molarities. Reference to table 4 also shows that the electrolytes of the some valencies, example NaCl and KCl, have almost equal values of the mean activity coefficient at the same concentration, particularly when the concentration is too high, not too high. This was the whole chapter. Thank you so much for watching.